This is the investigation of the adhesion of EPDM rubber and Kapton tape. I'm Katie White.
And I'm Eric Krementowski.
For about a year now, we have been working with Marmon Utility based in Seymour, Connecticut on the Carry electrical submersible pump motor lead cable. This is a layered cable with a conductive copper core, 2 layers of Kapton tape, which then receives a coating of Chemlock 250 adhesive, and then a layer of rubber is extruded on that. Customers have noticed inconsistencies in the adhesion of the rubber and the Kapton tape. Therefore, our goal is to improve the adhesion between these 2 critical layers. To do this, we will investigate the adhesive application method and what causes an uneven distribution. We will also investigate alternative adhesives with improved bonding, as well as testing methods to investigate adhesive strengths of these materials.
There are constraints involved with this project. These cables endure temperatures up to 450 degrees Fahrenheit, so the adhesives chosen must be able to maintain their properties at these extreme temperatures. The test data we gather also must be valid for a cylindrical product, as we are dealing with a cylindrical cable. We also cannot modify the cable layering structure except for the adhesive that we are presently dealing with.
To create the samples, we first roll out the rubber to a workable thickness. We lay out the Kapton tape and paint on the Chemlock or experimental adhesive onto the strip, then cut the long piece into approximately 6-inch strips to then lay in the mold. The piece of rubber is laid on top of the strips, and the whole mold is heat and compression molded for approximately 30 minutes at 350 degrees Fahrenheit. Next, the sheet is either die cut or hand cut into strips depending on what width is needed.
For the testing approach, we will be using a T-peel test, which there is an ASTM standard established for. The samples will be peeled vertically away from each other using the EPDM and Kapton as the substrates that will be attached into the grips and peeled, as can be currently seen on the right. We will vary the adhesive material using the initial Chemlock 250 as the control group, and we will be using a flat rectangular sample. These peel tests will give us results such as the ones shown here. The curve on the top will track the initial peak, the average load past the initial peak, the standard deviation of this average load, as well as the overall max peak, and this will allow us to understand the bonding strength of the adhesive as well as the uniformity of the adhesive deposition. From these curves, we will then create bar charts such as the one on the bottom of this page in order to compare all samples.
We are also able to perform an optical analysis on the samples after they have been peeled by using the program ImageJ. The images of the samples are turned into binary images and are analyzed to see what % of the sample is still covered in adhesive. This tells us if there is a cohesive or adhesive failure.
For future recommendations, there are 2 other types of peel tests that we have listed that we recommend to future groups. Along with this, there are several other adhesives and accelerated aging at high temperatures that we recommend. In conclusion, the testing data revealed that double coatings of the Chemlock adhesives did not perform better than a single layer of the adhesive, and also the narrow samples performed in a weaker manner than the wide samples. Overall, neither experimental adhesive provided superior results, leading to inconclusive results as to which adhesive should be selected.